Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Magnetic Ferrites and Applications from the paper Functional Materials. So students, let us discuss the main points which will be covered in this module. First, the three important categories of magnetic ferrites, that is, cubic spinel ferrites, hexagonal ferrites, and garnets are discussed. Second, properties of soft and hard ferrites are also discussed in detail. Third, various applications of magnetic ceramics will be explained. So students, let us start with a brief introduction about this module. The history of ferrites or magnetic oxides and their applications have been known for several centuries ago. The lodestone, that is manganite Fe3O4, which is a natural non-metallic solid, may attract iron. It was first described by the known Greek writings about 800 BC. Much later, the first application of manganite was as lodestones. It was used by early navigators to locate the magnetic north. This is the first scientific significance which was appreciated. After the first technical magnetic material, because it formed the first compass. The first scientific study of magnetism, named as D-manganite, was published by William Gilbert in 1600. Later, in 1819, Hans Christian Ørsted observed that an electrical current in a wire is affected by a magnetic compass needle. Naturally occurring magnetite is a weak, hard ferrite. Hard ferrites possesses a magnetism which is essentially permanent. Originally manufactured in a few select shapes and sizes, primarily for inductor and antenna applications, soft ferrite was proliferated into countless sizes and shapes for a multitude of uses. Furthermore, ferrites are used predominantly in three areas of electronics: low-level applications, power applications, and electromagnetic or EMI interference suppression. The breadth of application of ferrites in electronic circuitry continues to grow. The wide range of possible geometries, the continuing improvements in material characteristics, basically, and their relative cost effectiveness makes the ferrite components and the choice for both the conventional and innovative applications. Common ferrites. Basically, there are three important categories of magnetic ferrites. First is cubic spinel ferrites. For example, NiFe2O4, COFe2O4, and Fe3O4. Second is hexagonal ferrites. For example, BaFe12O19. Thirdly are the garnets. For example, R3Fe5O12. So students, we will be discussing all these ferrites one by one. Spinel ferrites. There is the FCC closed packing of anions. Secondly, we have the partial filling of interstices, that is, octahedral is 1 by 2 filled, tetrahedral is 1 by 8 filled. They are represented by the chemical formula AB2O4 or AOB2O3. Normal spinels examples are that ZnFe2O4, MgAl2O4, COAl2O4. Now, in the chemical formula, A is represented by the tetrahedral site and O is represented, or the B is represented by the octahedral site. The inverse spinels, for example, Fe3O4, NiFe2O4, having BaBO4, half of B are the tetrahedral, A and remaining B are the octahedral. S formula units per unit cell. Spinel structure. So students, here a general spinal structure has been shown where the bigger circles represents the oxygen atoms, then the shaded one represents a cation in the octahedral site, and the dotted one represents the cation in the tetrahedral site. So as you can see, the octahedral interstices where there are 32 per unit cell, and as compared to tetrahedral interstices, there are 64 atoms per unit cell. The atomic positions and the moments in the case of hexagonal ferrites. Out of 12 iron atoms in one formula unit, 9 occupy the octahedral sites, 2 occupy the tetrahedral sites, and remaining one is 5-fold coordinated. Out of these, 7 atoms on octahedral site and 1 with 5-fold coordination have their spins in one direction, while the spins of the rest of the atoms are oriented oppositely. That is, say 8 atoms with the spin up and 4 atoms with the spin down. As we saw earlier that each Fe3 plus ion has spin magnetic moment of 5 mu b. So, simple mathematics gives us a net magnetic moment of 20 mu b per formula unit, leading to a magnetic moment of 40 mu b per unit cell. So students, let us discuss about its magnetic behavior. It has a high degree of magnetic anisotropy. Second, it magnetizes relatively easy along the 0001 direction or C-axis of its unit cell. Lastly, it is categorized as a hard ferrite with coercivity between the 50 to 100 kiloamperes per meter, depending upon the microstructure and composition. In garnet ferrites, the orbital magnetic contribution of iron atoms is quenched due to shielding from crystal field, while lanthanide ions contribute to both orbital and spin magnetic moment, thus contributing more to the total magnetic moment. So this figure shows the crystal structure of a garnet structured compound on the left and the mineral on the right. Now let us discuss about the garnets. Garnets are usually known as minerals. Their general formula is R3Fe5O12 containing two magnetic ions. One is typically being iron and other is represented by R, which is the rare earth element. Here R, in addition to yttrium, can be the one of lanthanide atoms such as lanthanum, cerium, samarium, etc. Now let us discuss about its structure. The unit cell of Y3Fe5O12 is cubic and it contains 8 formula units, that is 160 atoms. Students, this is quite complex. Magnetic contribution is by first, the iron atom's orbital magnetic contribution is quenched due to shielding from the crystal field. Second, lanthanide ions contribute to both the orbital and spin magnetic moment, thus contributing more to the total magnetic moment. Magnetic structure of garnets. In this structure, our atoms have cubic coordination, that is 12-fold. Two Fe atoms have octahedral coordination, while remaining 3 Fe atoms have tetrahedral coordination with anti-parallel spin configuration of spins on tetrahedral and octahedral sides, while orientation of spins on R side is parallel to those on octahedral sides. We know that each Fe3 plus ion contributes 5 μb, which each lanthanide atom, that is R, contributes a moment of magnitude μr μb, where μr is the strength of moment of R ion, shows the total picture of how the magnetic moments in the garnets per unit formula. So here the net magnetic moment is 5 minus 3 mu r, the whole multiplied by mu b. The value of mu r is 7 for GD, while it is 0 for Y. Hence, the net magnetic moment, according to the above schematic, would be dominated by rare earth ions when mu r is greater than 5 by 3. Temperature dependence. Temperature governs the coupling between the rare earth and the iron ions. Typically, the net magnetic moment drops as the temperature increases, especially for strongly magnetic ions like GD, TB, and DY. GD doped garnet of composition Y1.2, GD 1.8, Fe5O12 has rather stable saturation magnetization for a wide temperature range centered around 50 degrees Celsius. Garnets can be quite useful materials in microwave applications because of their high electrical resistivity and hence lower losses around microwave frequencies. The material is also easy to synthesize in either of bulk polycrystalline ceramic, single crystal, or thin film forms. The structural parameters as well as magnetic properties can be tuned by tailoring the composition of the material. Properties of ferrites. So students, we have already discovered that the ferrites, they can have a broad spectrum of properties depending upon the type of ferrite and composition. This table shows some properties of common magnetic ceramics. These values are quite dependent upon the microstructure and the processing history of the material. For comparison, values for some common magnetic metals and alloys are also given. Soft ferrites. They are useful in microwave applications because of their high electrical resistivity and hence the lower losses around microwave frequencies. The material is also easy to synthesize in either of the bulk polycrystalline ceramic, single crystal, or thin film forms. The structural parameters as well as magnetic properties can be tuned by tailoring the composition of the material. Now let us discuss about the properties of hard ferrites. Hard ferrites or hard magnets, they have high coercive field of these materials, which is typically around 150 kiloampere per meter, and they are often called as permanent magnets. This is because these materials are able to withstand any demagnetizing effects that may arise either internally or externally. In addition to magnetization or remanence, BR and coercive field, a permanent magnet is often characterized by the product BH, that is area under the magnetic hysteresis curve. Remnants in the materials like hexaferrites, which are strongly anisotropic, can be affected by processing. Since the effect of magnetic anisotropy in a polycrystalline ceramic is small, the material can be synthesized under the application of a magnetic field, thereby aligning the moments along C-axis in the grains, giving larger remnants. Similarly, coercivity is a strong function of grain size, and it is found for hexaferrites that it is maximum for grain sizes of about 1 micron. Applications of magnetic ceramics. First is in electronic inductors, transformers, and electromagnets. Soft ferrites like manganese zinc and nickel zinc ferrites are used as core materials in these applications in the frequencies ranging from 100 kHz to 100 MHz. Typically, these ferrites have high electrical resistance, which results in a very low eddy current losses. Most common radio magnets, example in loudspeakers, are made of ferrites. Ferrites are also used for power transformers, which are used to transmit either over a single frequency or within a range, such as in ultrasonic generators. Next application is the equipment shielding. Here, due to their high impedance to high frequency currents, ferrite components of nickel zinc and manganese zinc ferrites are able to protect the equipment from high frequency electrical noise due to electromagnetic interference. Next application is the data storage. Example, magnetic recording tapes and hard disks. In the magnetic tapes, which is elongated 0.2 to 0.5 micron, long hard magnetic oxide particles of gamma Fe2O3 are embedded in non-magnetic binder. The particles have single domains magnetized along their major axes, which are aligned in the plane of the tape. In magnetic hard disks, core element is produced by forming several layers of materials. Here, the read-write head is not in direct contact with the hard disk due to an air bearing. Airflow is caused by the relative velocity between disk and head. Next type of application is the used as the absorbing material. In stealth aircrafts, ferrite particles are used as the radiation absorbing materials for low frequency applications such as 30 to 1000 MHz. Now the final application is the microwave application in the frequency ranges of 1 to 300 GHz. Materials like magnesium ferrites, lithium doped ferrites, and garnets are used for such applications such as phase shifters, circulators, and isolators. So students, let us summarize what we have learned in this module. First, while most ferromagnetic materials happened to be the metals or the alloys, many spinel structures, oxide ceramics, especially those which containing iron and other magnetic elements, example Fe3O4, which tends to be ferrimagnetic. However, there are other oxide ceramics such as hexagonal ferrites and garnet structured oxides which also show reasonably large magnetic moments. Second, these ferrites are useful for a variety of applications, introducing electromagnets, shields, data storage devices, and microwave applications.